Hi folks, this is going to be our third and final video on stereochemistry. I'm going to talk about a new type of stereoisomer called diastereomer. I'll talk about symmetry and chirality, and then I'll talk about cyclic systems. Recall that stereoisomers have the same connection of atoms, known as the constitution, and yet they are still non-superimposable. This is because their three-dimensional shape is different. We've previously talked about enantiomers, which are one subset of stereoisomers. These are non-superimposable molecules that are mirror images of each other. Here is an example of a pair of enantiomers. Both contain 6-membered rings, on which you have an OH group and a CH3 group on neighboring carbons. In one structure, I have a wedged OH group and a wedged CH3 group, and in this other molecule, I have a dashed OH group and a dashed CH3 group. If you assigned stereochemistry here, you would find that the chiral center with the alcohol on it has configuration R, while the chiral center with the methyl group on it has configuration S. In the other structure, both of these configurations have flipped. The one with the alcohol on it is S, and the one with the methyl on it is now R. Because the configuration of all chiral centers changed, you can think about that as all wedges went to dashes, that makes these two molecules enantiomers of each other. If you flipped over one of these molecules, you could make it look like the mirror image of the other one. There is another type of stereoisomer that we're just now going to encounter, known as a diastereomer. These are stereoisomers that are not mirror images of each other. Now let's consider these two molecules. I have a wedge OH and a wedge CH3 in the molecule on the left, and now in the molecule on the right, I have a wedge OH and a dash CH3. This is the same molecule that I'd drawn above on the left, and so the configurations are the same. R for the carbon with the OH group and S for the carbon with the methyl group. The chiral carbon with the alcohol group on it has configuration R, and the chiral carbon with the methyl group on it has configuration R as well. Looking at the configuration of each chiral center, notice that the configuration of the carbon with the methyl group on it has changed between these two structures, but the configuration of the carbon with the alcohol on it has not changed. These are two different molecules, they are stereoisomers, and yet they are not mirror images of each other. We would call these diastereomers. Enantiomers will always have all opposite configurations at their chiral centers. Compare these two molecules, which I will call A and B. To make it easier to describe how the configurations are changing between the two just by looking at wedges or dashes, I'm going to number both of these molecules, starting from the left. Notice that at carbon 2, molecule A has a wedged bromine, and B has a dashed bromine. And at carbon 3, you have a wedged chlorine in molecule A, and a dashed chlorine in molecule B. Notice all of my wedges in molecule A are going to dashes in molecule B. This means that all configurations are switching at all of my chiral centers, so A and B are enantiomers of each other. Diastereomers will always have at least one configuration in common, and at least one that is different. Let's compare two molecules that I will call C and D. These contain 3 different chiral centers. To give the substituents the lowest numbers possible, I'm choosing to number my chain starting at the right side. Let's look at carbon 4 of the chain. In molecule C, this is a wedged methyl group, and in molecule D, this is a wedged methyl group as well. At carbon 3, molecule C has a dashed methyl group, and molecule D has a dashed methyl group as well. It's at carbon 2 that we start to get differences. So molecule C has a wedged fluorine, whereas molecule D has a dashed fluorine. Notice that at chiral centers, carbons 4 and 3, you have the same configurations, and at carbon 2, you have a difference in configuration. Because you have one configuration that's different here, molecules C and D are diastereomers of each other. I want to show you some steps for drawing all stereoisomers for a compound. Let's look at this cyclohexane with an alcohol and a CH3 group. The first thing you'll want to do is identify all of your chiral centers. In this particular case, there are 2 chiral centers, and sometimes organic chemists will denote this with an asterisk. Your maximum number of stereoisomers that you could draw is 2 to the power of n, where n is the number of chiral centers you have in this molecule. So in this particular case, I have 2 chiral centers, so my maximum number of stereoisomers is 2 to the power of 2, or 4. Then you want to draw all possible configurations. One possible configuration has a wedged OH group and a wedged CH3 group. Another configuration has a dashed OH group and a dashed CH3 group. Another possibility is you have a wedged OH but a dashed CH3. Or you could have a dashed OH but a wedged CH3. These are my 4 different possible configurations, which I'll label A, B, C, and D. I'm going to look at these molecules to see which are my pairs of enantiomers. Notice that molecules A and B have all of their configurations changing. All wedges go to all dashes, so this is one pair of enantiomers. And actually, compounds C and D are enantiomers of each other too. Going from C to D, all wedges go to dashes, and all dashes go to wedges, so those are a pair of enantiomers as well. We could also look for pairs of diastereomers, or looking at which molecules are not mirror images of each other. It turns out that there are 4 possible pairs of diastereomers here. Molecules A and C are diastereomers of each other because they have one configuration in common and one different. And then we have 3 other pairs of diastereomers as well. In each of these diastereomer cases, your molecules that you're comparing have one configuration the same and one changes. Now that we have enantiomers and diastereomers, I want to revisit physical properties. Enantiomers have the same physical properties. Here is an example of a pair of enantiomers, and notice that they have identical boiling points. In contrast, diastereomers will have different physical properties from each other. Here's an example of a pair of diastereomers. These are not the same compound, and they're also not mirror images. And notice that their boiling points are different. It's not that their boiling points are the same, but one is positive and one is negative. They are just different numbers. This will always be the case for diastereomers. Now that we have molecules with more than one chiral center, I want to revisit the idea of chirality. Any molecule that contains a single chiral center will always be chiral. If instead a molecule has more than one chiral center, it will often be chiral, but it's not necessarily chiral. For molecules with more than one chiral center, you have to look at symmetry to determine if the molecule as a whole is chiral or not. A molecule that has more than one chiral center that contains a plane of symmetry within the molecule is an achiral molecule. And we term this type of molecule a meso compound. I'm going to show you 3 examples of molecules containing planes of symmetry. Here's an example where you have a 6-membered ring with methyl groups wedged on neighboring carbons. This molecule contains 2 chiral centers. You want to be on the lookout for whether or not you have a plane of symmetry cutting through your molecule. In this case, there is a plane of symmetry cutting through the middle of the molecule horizontally, and this plane of symmetry is perpendicular to the page. What I mean by a plane of symmetry is that the top of this molecule looks like a mirror image of the bottom half of my molecule. Because this molecule contains a plane of symmetry, it is achiral. And because it's a molecule containing 2 chiral centers and a plane of symmetry, we would call it a meso compound. Here's another example molecule to look at. First, you want to identify chiral centers. The 2 carbons, each with a bromine attached to them, are chiral centers. So we know our molecule contains 2 chiral centers, and now we need to determine, does it contain an internal plane of symmetry? In this case, there is a plane of symmetry present, and it cuts vertically through the middle of the molecule. Again, this plane of symmetry means that the left side of the molecule looks like a mirror image of the right side of the molecule. Because I have a molecule containing 2 chiral centers and a plane of symmetry, this molecule is achiral, and we would call it another meso compound. Let's look at a third example here where I have a 4-carbon chain with a wedged OH group and a dashed OH group. This molecule contains 2 chiral centers, and now I want to look for a plane of symmetry. As it's drawn, this molecule does not contain a plane of symmetry. However, we are not done yet. Before declaring that it doesn't contain a plane of symmetry, we need to check if it could contain a plane of symmetry if we rotated some of our carbon-carbon bonds. What I'm going to do is keep the left half of the molecule fixed and rotate around only the right half of the molecule. After this rotation, my molecule would look like this. My left side looks the same, but now my methyl and my OH group have changed places, and when I flipped the dashed OH group up to the top of the page, it became a wedge. In this new conformation, my molecule does contain a plane of symmetry, cutting through the middle of the molecule vertically. Because this molecule contains 2 chiral centers, and there's a conformation in which it contains a plane of symmetry, this is another achiral molecule, and we would call it a meso compound. Be careful, not all achiral compounds are meso compounds. The molecule has to have more than one chiral center and yet be achiral in order to classify as meso. Now I want to revisit cyclohexanes. Here I've drawn out one chair conformation of a cyclohexane, and each of the substituent positions off of it. The substituents that are pointed straight up or straight down off of the cyclohexane are the axial ones, and the ones that are pointed out away from the ring toward the side are equatorial ones. Now I want you to imagine looking at this molecule from a bird's eye perspective, high up on the page. Notice these three axial groups are pointing up at you, and the other axial substituents are pointed down, away from you. Although the angling isn't so extreme, there are three equatorial positions that point slightly up toward your bird's eye view. And then there are three equatorial positions angled slightly down away from this perspective. Notice that each carbon of the cyclohexane contains an axial and an equatorial substituent, and each carbon contains an up group and a down group. I want to talk about a special type of stereoisomerism for rings known as Cis-trans stereoisomerism. This will come up when you have more than one substituent coming off of a ring. We'll call the cis-isomer the one in which your two or more substituents point toward the same face of the ring, either both angled up or both angled down. And the trans isomer will have the substituents pointed toward opposite faces of the ring. If you had two, this could be, for example, one up and one down. Here are some examples to consider featuring cyclohexanes. You can think about wedges as pointing up. In this case, my molecule contains two wedges off of the cyclohexane. So you would say that those substituents are both pointed toward the same face of the ring. And we would call this a cis isomer. In the other case, one methyl group is pointing up above the ring, and the other one is pointed down below the ring. Because these methyl groups point toward opposite faces, we would call this a trans isomer. If we wanted to be more specific, we could number the atoms of our rings. You would want to make the substituted carbons 1 and 2. We could be more specific and say that the relationship between our substituents on the left is that they are cis to each other and they have a 1-2 relationship. And in the other case, we would call this a trans 1-2 relationship. Thinking back to earlier in the video, if we wanted to describe the stereochemical relationship between these two molecules, I would describe them as diastereomers. They are stereoisomers that are not mirror images. When we're talking about disubstituted cyclohexanes, in order to draw chair conformations, we're going to need to consider the three-dimensional substituent orientation. Here's an example molecule where I have a 1-2 relationship of substituents. I have a wedged chlorine and a dashed methyl group. You can think about wedges as pointing above the ring in an up orientation, and dashes as being below the ring in a down orientation. The chlorine wedge points up, while the methyl group points down. Now we're going to draw chair conformations, and there's something I really want you to pay attention to. When you draw your different chair conformations and show the ring flip, you can change axial and equatorial, but you never change up and down. The chlorine wedge will always be angled up, whether it's axial or equatorial, and the methyl group will always be angled down, regardless of whether it's axial or equatorial. So let's start by numbering our carbons. I'll make the carbon with the chlorine 1 and the carbon with the methyl 2. I like to start by drawing two different chair conformations without the substituents drawn yet. For the chair conformation in which the upper right is the highest point on the page, I will always label that number 1. And I will always draw for the chair conformations where the upper left is the highest point on the page, I always put carbon 1 at the lower right. I just like to pick this method and use it every time. So now I need to think about where are things in my molecule, and looking above, I have substituents off of carbons 1 and 2. I know that my chlorine points up, so I need to draw my chlorine pointed up in my chair conformation. At this particular carbon of the cyclohexane, it is the axial group that points up. Coming off of carbon 2 is a methyl group that's drawn as dashed above, so it needs to be pointed down. Given the numbering system I created, at position 2, my down group is axial as well. Now I need to draw my other chair conformation, and my chlorine still needs to point up. My up group at this one position is equatorial, and at 2 I need to draw my methyl angled down. This 2 positions down group is equatorial. Notice in one chair conformation, both the chlorine and the methyl group are axial. And in the other chair conformation, they are both equatorial. Notice that, like we saw before when we had a single substituent, the ring flip is changing axial and equatorial. My chlorine was axial in one chair conformation and then equatorial in the other, and the same goes for the methyl group. What doesn't change is up or down. Notice that chlorine is angled up on the page in both chair conformations, and the methyl group is angled down in both chair conformations. To practice, I want to do another example of drawing both chair conformations, where now I have a different placement of different substituents. In this case, I have a wedged ethyl group, and 2 carbons away, I have a dashed methyl group. Before drawing chair conformations, I need to identify the relative positions as well as the up-down orientations of the substituents. I would number my cyclohexane ring from 1 to 6. Because the ethyl group is a wedge, it's pointed up, and because the methyl group is a dash, it's pointed down. Then you'll want to draw your chair conformations. I recommend numbering the positions and then fill in your substituents, taking into account the numbers as well as up or down. Again, I use the same numbering system where this top right position is carbon 1, and then carbon 1 moves to the bottom right in the other chair conformation. So let me start with the ethyl group. The ethyl group is at carbon 1, and it needs to point up because it's a wedge. At carbon 1, the up position is axial, so I've drawn this ethyl group as axial up. Now I need to draw my methyl group at carbon 3 and make it angled downward because that's a dashed methyl. At position 3, it is an equatorial position that's angled down. So I've drawn this methyl group at an equatorial down position. Now we can do the same thing for the other chair conformation. In the other chair conformation, the ethyl group still needs to be angled up toward the top of the page, but at this particular position, that's an equatorial site. And the methyl group, because it's dashed, still needs to be pointed down toward the bottom of the page. And at this particular 3 position, this is an axial down site. So notice here as well, I had an ethyl group that's axial in one conformation, and then it becomes equatorial in the other one. And my methyl group, which is at the 3 position, goes from equatorial to axial upon the ring flip. What did not change is what's pointed up or down. I want to end by talking about relative stabilities of different chair conformations, where you have more than one substituent present. One scenario is that both substituents happen to be axial in one chair conformation, and both happen to be equatorial in the other chair conformation. Here's an example where this happens to be the case. I have methyl and ethyl groups on neighboring carbons, where the methyl is wedged and the ethyl is dashed. Here I've drawn the 2 different chair conformations possible. I was careful to put the methyl and the ethyl on neighboring carbons. The methyl is always pointed up because it is a wedge. So in one chair conformation, it's axial up. In the other chair conformation, it's equatorial up. Then the ethyl group is always down because it's a dash. In one chair conformation, it's axial down, and in the other, it's equatorial down. Notice my structure on the left contains 2 axial substituents, and my structure on the right contains 2 equatorial ones. The structure in which both substituents are equatorial is more stable. This structure minimizes 1,3 diaxial interactions. I could draw in an equilibrium arrow favoring this more stable side. A situation that will require more nuance and thinking about substituent sizes is if you have 2 substituents, and in each chair conformation, one of them is axial and the other one is equatorial. Here's an example where this will be the case. I have a wedged methyl next to a wedged ethyl group. Because both substituents are wedged, they will both always point up. But in one chair conformation, methyl is axial and ethyl is equatorial. Then in the other chair conformation, methyl is equatorial and ethyl is axial. So each conformation has 1 axial substituent and 1 equatorial one. If this is the case, we need to consider the relative sizes of these different substituents. A methyl group is smaller than an ethyl group. And because 1,3 diaxial interactions are more severe with larger groups, you're going to prefer to put your larger substituent equatorial. On the left, we have the smaller methyl group axial with the larger ethyl group equatorial, while in the right structure, we have the larger ethyl group axial and the smaller methyl group equatorial. We favor placing the larger group equatorial, so the left structure is more stable. You could end by drawing in an equilibrium arrow favoring this more stable structure. Alright, so to summarize, this video talked about the difference between enantiomers and diastereomers. I talked about cis-trans stereoisomerism for disubstituted rings, and I talked about drawing chair conformations for disubstituted rings. That's it for this video. I'll see you in class.